Hi everybody, I am very pleased to share this moment with you. This talk is about enumeration and more precisely about enumeration of Cartesian products. This is joint work with Bruno Courcel and Michael Raskin. Why do we need enumeration for? Enumeration is essential when we deal with infinite sets of objects or with sets that are too big to be represented in extenso. See, for instance, the range operation in Python that used to generate a list in Python 2 and now produces an iterator in Python 3. In computer science, enumeration is used for such problems with large answer sets or queries on large databases. See, for instance, iterators in Java and SQL, and also in satisfaction problems and other problems of this kind. Myself, I felt the need for enumeration when I was working on my research project, which is about terms, term rewriting systems, term automata, and graphs. The system is entirely written in Common Lisp, and there is now a web interface developed by Michael Raskin that uses some JavaScript. I started the enum package about 10 years ago. It remains self-contained. The first version was presented at ELS 2012 in Zadar. I will first explain what I call an enumerator, then I will present the enum package. I will show the problems raised by the enumeration of products. Then I will present bidirectional level enumerators that solve these problems for enumerating products. So an enumerator is a state machine which outputs one at a time the elements of a sequence. Sequence may be finite or infinite. Here's some examples of sequences. Finite sequence of the weeks of the day from Monday to Sunday. Sequence of all natural integers. Alternating sequence 1 minus 1, 1 minus 1. The sequence of prime numbers, also infinite. There are two basic operations on an enumerator. The first one is a predicate, is there a next element? And the second one is give me this element and move to the next one. So this is the API for an enumerator. Every enumerator will be an instance of the abstract enumerator class. And these are the two basic operations, the predicate, which says whether there is a next element, and the operation that gives this element and moves to the next. These two operations can be combined into a single one, which returns two values. The second one indicates whether there was a next element, and the first one is the next element when it exists. Here an example. Here I make an enumerator of a finite list, ABC. So the first element will be A. Then there will still be an element, so next element returns T. There is still a next element which is B. I can combine these two last operations using call enumerator. So yes, there was a next element and it's C. If I call again call enumerator, then I will obtain nil because there was no more elements. We have this operation collect enum, which will collect all the elements of a finite sequence. But I can also have infinite sequence. Like here, I can make an infinite sequence of AB and for AB by making it circular with this keyword. Then I have the collect and enum operation to extract a finite sequence of the end first elements of the infinite sequence. There are two kinds of enumerators. The simple ones that are built from scratch that do not rely on other enumerators, like the constant enumerator that always enumerates the same value. Enumerators of elements of a Lisp sequence, like a list or a vector. Enumerator of a sequence which is defined inductively. We will see some examples later. And we have the composite enumerators that I call relying enumerators because they rely on other enumerators. For instance, the sequential enumerator will enumerate first all elements of sequence 1, then sequence 2, and so on. We will see later example of the parallel enumerator. Filter is like remove if in Lisp, and product, we will talk about product later. So the example of the parallel enumerator, it works a bit like the mapcar function. So it takes a function and then lists, and it will apply return the list of the values of the function apply to the tuple consisting of all first elements of the list, second element of the list, third element of the list, and so on. So instead of returning the list of these values, it returns an enumerator of these values. Time to talk about injectivity. So sequence is an application from natural integer to some domains, which maps an integer to a value of the domain. A sequence is not necessarily injective. We may have identical elements with different indices. For instance, the alternating sequence that we had seen before. For simplifying the proof, it is easier to assume that enumerators are injective. And this yields no loss of generality because a non-injective enumerator may always be transformed into an injective one by putting it in parallel with an enumerator of the natural integers. This is what we are going to see now on an example. So here I build an enumerator for enumerating the natural integers. It's an inductive enumerator. The initial value is 0, and this is the function to compute the next value from the previous one. So it's an infinite enumerator. I can obtain a finite part of it using the collect and enum operation. Now I put it in parallel with the enumerator of the list ABC that we have seen before. So this is going to be a finite enumerator because we stop with the shortest sequence, and the shortest sequence is finite. So collect enum will return 3 values, which are the values of ABC prefixed with the index. Now I can do the same with an infinite enumerator. So I put in parallel the natural integers and the constant enumerator, which always outputs the value A, and I obtain an injective enumerator which enumerates A's prefixed by the index. This is the implementation of the map function using enumerators. It's in the paper, I'll skip it, and I would rather present this other example, which is not in the paper. It's Eratosthenes sieve, which is a sieve to obtain all the prime numbers. So it consists of an enumerator which contains an enumerators whose aim is to filter all multiples of the primes that have been output so far. So this is a nice way to program this sieve. So here I can get the first 10 prime integers, and if I put here init nil, I will obtain the next 10 prime integers, and so on. So here a picture of all relating enumerators. So now we are going to concentrate on the product enumerator. So the product, suppose we have P non-empty injective enumerators such that each EI enumerates the sequence which may be infinite, finite, or infinite. So the TP is the Cartesian products of the elements of these sequences. TP contains tuples of length P, and each tuple contains an element of each sequence. If all the EIs are injective, then the tuples with distinct indices will be distinct. And if every EI is finite, the cardinal of the Cartesian product will be finite, otherwise it's going to be infinite. There are multiple ways of ordering this Cartesian product TP. So multiple possible enumerators of TP. So which order of TP would we like? First, we would like a fair ordering of TP. We would not like this kind of picture where we move only on one infinite enumerator and not on the others. So we would like an ordering which moves forward regularly on all enumerators. So this is what I call an unfair ordering of the product of natural integers and the finite list ABC. We would rather want a picture like this, a diagonal ordering which will move forward regularly on all enumerators. So this product, diagonal binary product, was already in the 2012 version. It gives the following result. Note that to implement this diagonal ordering, we need the enumerators to be able to go backwards. When I go, for example, on this step, the enumerator, the y enumerator on the y-axis is going down, and the x enumerator is going up. And it's the opposite when I'm here. It's going backwards on the natural integers and forward on the ABC enumerator. This is why we need bidirectional enumerators, which I'm going to present now. So a bidirectional enumerator can move forward and backward. So it has a way, an operation to deal with the way. The basic operation are not next element P and next element, but way next element P and way next element. They say, give me the next element in my way, in the way I am right now. So I can always make a bidirectional enumerator from a non-bidirectional one using this operation. And here, so I have a bidirectional version of the enumerator of the natural integers. So by default, the way is initialized to forward, which is 1, and backwards will be -1. So if I call for the next element, I will obtain 1, 2, 3, 4, and so on. For implementation, I need the operation that gives me the latest element. So here the latest element is 3. I can force locally the enumerator to go in another direction, so here to go backwards, then I go back to 2, but the way is still 1, so next time I obtain 3. Now if I want to change the way of the enumerator, I use this operation invert way, and now the enumerator will go by default backwards. So from 3 to 2, from 2 to 1, locally I can ask the enumerator to go forward, but it's still going backwards. So next one will be 1. So using these bidirectional enumerators, we can program the diagonal binary product. If both enumerators are infinite, then it's quite simple. We have the normal steps, which are the diagonal steps. One is going forward and the other one is going backwards. And we have those special steps when one of the enumerator reaches its bottom, then we have to do here a sliding step. So here on the wall and change the way of both enumerators. So they both change way. It's a bit more complicated when we have finite enumerators. In this case, we may have an additional case, which is when one enumerator reaches its bottom and the other one its top value at the same time. Then we have what we call corner steps. Here with the dotted line, this is a corner step. Now I need the notion of distance between two tuples. So it will be the sum of the difference between the distance between two tuples will be the sum of the differences between the indices. But to simplify, from now on, we assume that every EI enumerates integers starting from this 0. So the list of indices will be the same as the tuple. So the distance between two tuples will be the sum of the distance of each component. So here, between here and here I have distance 1 because I have distance 1 for the first component and 0 for the second component. Between these two tuples I have distance 2 because here I have distance 1 for the first component and distance 1 for the second component. 1 plus 1 gives 2. You have to see each enumerator of the product like a wheel of a mechanical counter, which the wheels can be moved forward or backwards one or more times, and the distance between two tuples, it's the number of moves, or the sum of the size of the moves of the wheels to reach the next configuration. Now I call a deordering when I have a step. When I go from a tuple to the next tuple, the size of this step will be the distance of the two tuples. And I call an ordering of TP is a deordering if each step is at most D. Our aim is to have a two ordering of TP. For P equals 2, we already have 1 because as we have only two enumerators which go at most one notch forward or backwards, the sum cannot be more than 2. In fact, there exists one orderings for P equals 2, but they are not feasible in our setting because they assume that we have a look ahead of 2. Here we cannot know whether we have a next element of a next element without moving to the next element. So they exist, but they are not feasible in our setting. So we'll concentrate on two orderings, and this is our aim. So we have the binary product, which is a two ordering, but if we use recursively this binary diagonal product, we don't obtain a two ordering but a p ordering. So this is an example of binary product with natural numbers and 0, 1. So this one is a two ordering because it's binary, but if I combine it, this one, and I multiply it here by this other enumerator, then I will obtain here a step that has distance 3. This is this red step here when we go back here. And it's possible to show that if we have P equal, that this recursive use will give a P ordering and not a 2 ordering. So to achieve a 2 ordering, we need an additional notion, which is the notion of level. So the level will be a subset of tuples with identical height, and a height of a tuple will be the sum of the indices of the elements in the tuple. Not that in our case it's going to be just the sum of the elements of the tuple. So the height level of TP will be the set of tuples with height h, and we denote this level by LH. So an ordering of TP is leveled if it traverses the levels in increasing order of levels. So first L0, then L1, and so on, without constraint so far on the order of enumeration inside the level. So level enumerator will be an enumerator of a product that follows a level ordering. We'll call a step giving a change of level when we go from level I to level I plus 1 will be called a major step, and a step inside the level will be called a minor step. So level enumerators have an additional predicate, which is minor step P, which says whether we are going to do a major step or a minor step. Now I have bidirectional level enumerators. So they are both leveled and bidirectional. When they go forward, the levels are enumerated in increasing order. Level 0, level 1, and so on. When they go backwards, the levels are enumerated in decreasing order, Li, Li minus 1. But inside the level, it's the same order. So here is an example. So I have here binary product of 0, 1, 2, 0, 1, 2, and this is the bidirectional level enumerator that I build. So I do first level 0, then level 1, all tuples 1, 0, 0, 1 is level 1, all levels 2, and level 3, and until here, yes, until here, and level 4 is if I change the way I will start enumerating the levels in reverse order, so level 3, then level 2, then level 1, then level 0. But inside the level, you see it's the same order. Here we have level 3, 2, 1, 1, 2, and here level 3, 2, 1, 1, 2, although we are going backwards. So using these bidirectional level enumerators, we can define a product. So we define this product. Here, X on the left is going to be a normal bidirectional enumerator of one of the enumerator of the product, and on the right I will have a bidirectional level enumerator. So the product works a little like the binary product. We will have diagonal steps, which will be minor steps. We will have major steps that will be either sliding or corner steps. And they will, depending on the way of the enumerator, the main one, the level increases or decreases by 1. Okay, this is the code to implement it. We have to implement the way next element operation, and then it includes normal steps, sliding steps, and corner steps. So by construction, this product is bidirectional, and we can show by proof, this is in the paper, that this product is leveled, so that if Y is leveled, then this one is also leveled. Moreover, we can prove that if this one is a 2 ordering, then so is the product. So now, using this binary product, we can build a bidirectional level enumerator for the Cartesian product TP. So here we put all the enumerators of the product, and we combine them with the bidirectional level product. And we put here trivial enumerator that enumerates just one tuple of length 0. So we can now do a proof by induction to show that this is a level enumerator and a 2 ordering. So we have reached our aim to have a 2 ordering of the Cartesian product. So this is an example. So not here the strange steps here. This is a minor step on the higher level, so the X is going forward because we go from 0 to 1, and the Y is going backwards. It makes a major step of -1 because we go from 2, 0 here to 1, 0 here. So this is a major step backwards, while the other one does a major step forward. So it's a minor step on the top level. So this is the end. So we have reached our aim to have a 2 ordering of the Cartesian product using recursive use of bidirectional level product. Now we need a non-recursive version to avoid stack exhaustion. The enum package, it's now about 2,300 lines. It's still self-contained but not yet available separately. Thank you for your attention.